A very good morning, Shubhodaya and Namaste to everyone who has logged in. I'm Pavithra. I work as scientist here at CSIR 4PI and I welcome you all to Vismaya Vigyana, a 3-day lecture series by CSIR 4PI Jigyasa members. Just last week on February 11th, we celebrated the International Day of Women and Girl Child in Science. In spirit of that, Jigyasa team members have planned to conduct a 3-day Science YouTube webinar series starting from today, 18th February, lauding the spirit of Indian women in science and technology. Jigyasa literally means to build an interest in science among the student community, and it is our pivotal goal. This concept of Jigyasa or the project of Jigyasa was penned under the leadership of Dr. Narendra Modi ji. The agenda of today's webinar is we shall begin with a talk from Dr. Sridevi, our head of CSIR 4PI, and her topic is Paradigms of Science. Next, we have our in-house senior principal woman scientist, Dr.Sajani Surendran, who will be here to speak about physics of Indian summer monsoon. I really hope that each and every student logged in here shall make full use of this opportunity. I welcome Dr. Sridevi Jade and Dr. Sajani Surendran to the webinar. Thank you, ma'am. Thank you for agreeing to do this. Sridevi, ma'am, the dais is yours.
Yeah. I'm audible?
Yes, ma'am.
Okay. Good morning. Welcome to whoever is watching. Actually, the internet, like she has said, the International Women's Day was on February 11th. So we had a webinar that day. CSIR had a webinar that day. Now CSIR-Fourth Paradigm Institute. We are having this webinar series starting today and it goes on till Wednesday. So whoever is interested can watch it. So I will basically, the job given to me is because as the head of the institute is to talk about our institute, which is Fourth Paradigm Institute. So to talk about our institute, first I have to talk about the paradigms of science. So that's how this title came, on paradigms of science. I would take around max 15 minutes and then hand it over to Dr. Sajani Surendran, who is the main talk of this day. I am only here to talk as the head of the institute. So with these remarks, I will share my PPT. You can see my PPT?
Not yet. Not yet.
It says it is shared now. You can see?
No, not yet.
Okay, I'll share again. Close. Stop sharing. There. Window. Now?
Yes. Yes, ma'am.
I'll go to slideshow mode. You can see the slideshow mode?
Yes, ma'am. Yes, we can.
So, I will talk about basically paradigms of science. So, the moment we say science, the thing that comes to our mind is maths and physics. So, we'll start from there and then we'll go to paradigms of science. So, actually speaking, maths is the one and only standalone science. Because, that is the one science which is as ancient as humanity. As ancient as humanity, which started with like counting of numbers and then calculations, then shapes, objects, measurements, and then you come to writing equations, then come to abstract mathematics. So maths, then comes the physics. The maths and physics are used in tandem for scientific application, astronomy, and for philosophical applications, everything. So basically, maths is a tool for physics, and Physics gives insight, they complement each other. Physics gives insights into the mathematics. So this is the science, definition of science. Then coming to paradigms of science. Currently we have 4 paradigms. I think everyone else should be on mute. There is a resound. Please mute yourself. Pavithra. Sajani, you have to mute. Both of you. There is a resound. Okay, so who's not mute? Pavithra, you have to mute. Resound is coming.
I just unmuted, but I'm on mute.
Okay. So there are currently 4 paradigms of science, as my slide shows, and there is an emerging 5th paradigm of science. See, it's not anything like very big definition paradigms of science. It's as simple as that. When we do discovery through observation of nature, that is basically your experimental science. When we do, and I will give you examples of each one of them. And then the second paradigm is when we use equations to whatever we observe, we write equations, solve them both empirically and analytically. That becomes the second paradigm of science. I have also given the timelines in my slide. And when these equations and our observations become very complex, observations become huge and equations become complex, then we have to use computers to solve these equations. So that is the third paradigm. And the fourth paradigm is big data science. That is basically data intensive scientific discovery. We will come to it. I'll explain in detail what it is. And also I would like to say there is an emerging 5th paradigm of science when basically artificial intelligence dictates us what to do. So that becomes our 5th paradigm of science. So I just give simple examples so that everyone can understand, because this is supposed to be for school children up to 12th standard. So this is the first paradigm. Simply we sit and we keep watching. I have taken stars and astronomy as example because that relates to students much easier than anything else. So my slides mostly talk about looking at stars, gazing at stars and telescopes. So this is the first paradigm. So when we look at stars, we count stars, and then every night we see the star, how it is changing, how it is moving. So these are all observation through nature, through which we come with discoveries that ancient Indians used to do. Then we come to the second paradigm when we start looking through a telescope. So the moment you have a telescope, then your physics and maths comes to play. You would have formed some theories, solved some equation to build the telescope, but still you are looking at the stars and collecting data. But then the telescope comes under the second paradigm of science. Then you have the third paradigm of science. When you have a very complicated telescopes, like this picture which I have given is an infrared telescope at Hanle in Ladakh, Himalaya, which is at a height of around 4,500 meters, and which is a very rare, very clear skies. Though here you can see a lot of clouds, but usually clear skies. And it also has very minimum water vapor so that the infrared rays don't get affected and you get a clear view of the sky. Actually, if you stand there, I've been to this place, you can see the galaxy, Milky Way and all very clearly in the night with naked eye. So this is the infrared telescope. This comes under third paradigm of science because this involves computers and all that to build it, and also the data that is collected through it has to be analyzed through computers and all to get some tangible results. So this is the third paradigm of science, and this telescope actually is monitored remotely. Though it is in Ladakh, Himalaya, it is monitored from Hoskote in Bangalore. They have an observatory. This belongs to Indian Institute of Astrophysics. And we are working with Indian Institute of Astrophysics since 1997. We have an MOU with them. And this telescope was set up in 2001. This is the third paradigm. Then comes the fourth paradigm. This is the recent picture of July 2021. So, it's like some telescope, gamma ray telescope. Yes, built by so many institutions, BARC, TIFR, IAA, ECIL and all that. So, if you can see me, this is me standing here. So, that shows the size of this telescope. I think it is 21-meter radius telescope, and these are the panels. Some 300 plus panels are there which are looking at the sky. And this is the room, observation room with computers and all, where the data is collected. So this comes under fourth paradigm of science. So the data that is collected through this telescope basically can be used for several applications. I will simply give you one simple application which I read yesterday, which was published in Royal Astronomical Society as a news item, is that they basically, like this, you have observatories, so they collect data on planets, galaxies and all that. So right now the current this thing is the number of planets are much more than the stars in the sky. So if you want to find out whether there is any planet like Earth which is inhabited by any kind of living beings, so what they are trying to do using data science is, they basically train a machine. See, they give some features to our planet Earth, which is variables and features to our planet Earth, which is inhabited by us. So, and train the computers through machine learning on this aspect of inhabitants on a planet. Then they have written an AI algorithm which goes through all the data, worldwide available data on planets, and then it goes through and tries to figure out if any of that has is inhabitable, or there are some people living on it, or some living creatures like that. So this is your fourth paradigm of science, that is data intensive scientific discovery. So you use AI and ML, which will come to that later. So this is the fourth paradigm of sciences. So basically our institute, this paradigm of science needs petascale computing and large storage, and then you have a completely new field. See, earlier we had you have a field like you say geology, okay, study of rocks and all. Now you have a computational geology like that, astronomy, then you have computational astronomy, because now data science has become a discipline in itself. So this is what is called fourth paradigm, and we are called the Fourth Paradigm Institute. We are set up to basically do research in data science. Then coming to data science, I just thought I'll give a glimpse to the students on some aspects of data and science. I think there are some 3-4 slides on it. Whatever I just now gave you as example, I've given here. This is what is Wikipedia definition of data science. Basically uses scientific methods, process, algorithms and systems to extract knowledge and insights from noisy, structured and unstructured data. Okay, then we use these insights for broad range of application domains. Like just now I told you an example where we are trying to find out if any planet in the galaxies is inhabitable. So that also comes under this. So there are two kinds in data science. One is when you are searching for needles in a haystack. That is, you are searching for some kind of anomaly in the data. This is a structured thing where you have an index database, and you want to identify a particular star with a particular property. This is straight away thing, like we use statistical tools. Of course, they are complicated, and you still can find out. Okay, so and this is kind of like, you can say, deterministic, something which you would definitely find out. But sometimes the data itself tells, you look at it, there is a trend analysis that itself gives you some kind of discovery. That comes under data mining, AI and ML. Just now I gave you an example. So the difference between AI and ML is, AI is basically, it creates intelligent machines capable of simulating human behavior. That is, like when you are searching for a inhabitation on a planet, your AI behaves as if a human has gone there and seen it, and he saw people living there and he's coming back and telling you. That sort of thing. Whereas machine learning is a subset of artificial intelligence where you train the machine with all the data you have. So these are the two things in data science which I thought all students should understand in the simplistic form. So, like we always say, in our ancient India, everything was there, or whatever science is now there. See, we had Pushpak Vimana then itself like that. But those were not backed by any scientific data. But this we can take some credit that our data science was available during ancient Indians, because it was also studied and published by Professor Rodham Narasimha, who was earlier director at NAL Bangalore. So basically what he has, there's a book written by him, and if somebody is interested, they can look into it. This basically what it says is, in our ancient approach, whatever computation we make, we match it with observation. Like now my data predicts there is some sort of living life on a particular planet. But then your observation should be, you should be able to go and see it physically. So that kind of thing was the ancient approach, like you compute and then match with observation. But what AI, what we do in that is not actually practically possible. So what we are doing predictions, basically by using logic, models. Again, we take the same example of life on a planet, then we go through algorithms and then we say, okay, there is life on this planet. So that is called quantitative prediction. So this would work for a natural phenomena where patterns are regular, repetitive and all. But like, you can check it out. Like you do, for example, you do data intensive scientific discovery for any natural phenomena, predict it like a cyclone and all. And then you can always say that this matches with the observation when it occurs. So that is where it is repetitive, regular kind of approach. But when it is completely random, then it becomes really hard. That is the challenge. And also when it becomes random in a man-made world, you have overload of information. So applying data science requires lot of knowledge and care and all that. And also there is a lot of intentional misuse of data science. So what we should answer is what rather than how. So that is what is this thing. See, my next 3 slides are actually, I heard a lecture by Professor Haritsa from IISc Bangalore, who had given a lecture in our organization for Foundation Day. So next 2-3 slides are basically derived from his lecture, the thoughts he put and the thoughts little bit I had together I have put. So is data science a boon or a bane? So as far as I am concerned, it is both, because you can do lot of science using this which you could not have done earlier. But then it is a bane in the sense, I will tell you what happened. So, it is very good for supply chain management, inventory management, like the big like Amazon, energy sector and all benefited hugely by it. And of course the health sector, which is very important for humans. So in terms of imaging, robotic surgeries, etc. And in science, astronomy, earth sciences, because astronomy is one field where we really need data intensive science, because then only you get to know what is happening, planet system, science and all that. And of course, you all must be aware of the target advertising. Like when you go to watch something on Netflix, it tells you based on your watching patterns, what you would like. It will suggest what you should watch. Or you go to your web browser and try to purchase something. Next time you log on to the web browser, it will suggest you what you should purchase. So that is target advertising. So it is very effective for such predictive models which are repetitive and with very good, strong quantitative confidence. So now I will come to one example. Recently that happened. So I would ask, what is the connection between Lata Mangeshkar, who recently passed away, which is a very sad thing, and New York Stock Exchange listed DD Global, a mobility platform company in China. So I will tell you the connection. After the demise of Lata Mangeshkar, the shares of this company went up by 20%. So people are wondering, where is the connection? The connection is this. We call Lata Mangeshkar very fondly as Didi. Okay, so when she expired, the news coverage, both national and international, was very high on social media everywhere, saying Didi, Didi, Didi. And this New York Stock Exchange, they market how their stock is performing, Didi Global, on a ticker word, the crime word as DD. So whenever the DD appears in the news channels and all, it's picked up by the ticker. So it basically showed that there's a lot of interest for their stock, and then globally, internationally, and then people started buying it. So this is one of the things a data science is capable of doing without any intervention from humans. So though there is no actually connection, their stock went up and there was 20% rise in the stock. But then in that process, some small players would have lost because this is a fake thing. This really their stock didn't go up. So it has its both advantages and disadvantages. So basically the data science, what we should give more importance in data science is the word science. It should be solidly backed up by the domain science for which you are applying the data, big data analysis. So there should be a strong understanding of physics. We started with maths, physics, so strong understanding of physics, maths, than data mining and programming. So like, Professor Haritsa was saying, this is a quote by a Nobel laureate, if you torture the data long enough, it will confess to anything. So, nowadays we can see this kind of misuse of data heavily, not intentional, but it happens because the data scientists feel that they know everything. Like we have seen last 2 years of COVID pandemic, how many predictions have come and how many of them said how many things, and there was so much overload of information at the end of the day. We didn't even know what is genuine in that. We just gave up. So that kind of use of data science is a bane. It does not help anyone and it's not good also. So like I said, my conclusion is that it's like nuclear power. You have enormous potential, but then it should be used properly. Anything in this world, when it is used properly with solid concepts and background, is always a boon to the society. But then how much it is applicable in today's practical world is questionable. And also the offset of this data science is you need huge computing systems and huge data storage. Actually, it is estimated at 30% of our energy costs globally. So that's a really huge number. So we'll have to think about this also when we talk about data science. Then coming to this finishes my talk on paradigms of science. I just give a glimpse of our organization in 5 slides. So we belong to CSIR, Council of Scientific and Industrial Research. As you can see in the map, you can see lot of, these are all our institutes, around 37 institutes. Then we have outreach centers, then units. So we are an institute located in Bangalore in the NAL campus. We are located within the NAL campus. And CSIR actually works on, it's a very huge field, wide spectrum from oceanography, geophysics, drugs, genomics, environment, information, nanotechnology, engineering. There's so many fields. And we also have an academic wing called ACSIR, which functions as an academic institute. It's a separate vertical. And we are ranked around 37 globally, and we are only Indian organization in the top 100 global government institutes. And we are also ranked 7th in Asia. So this is what we do. This is about our institute. We were established in July 1988 as a 3rd paradigm institute. Then we got repositioned as 4th paradigm in 2013 to do big data science. So what you can see here, this is our prediction of extreme temperature and thunderstorm with a 78 lead, 48-hour lead. And this is seismic risk and all that. So that is one. So we have 2 divisions. One is Earth and Engineering Sciences, one is Data Science and Supercomputing. So as you can see this figure, this is what we have plotted. These are all the earthquakes of Indian subcontinent using the data from ancient till now. And this figure, if you see, we have a cybersecurity test bed. These red, orange dots you are seeing are the malicious connections captured by them in a period of 1 week. So each dot is cluster of computers which are trying to attack the cyber security network. So this is the other thing. So these are some of our results. We gave the first deterministic seismic hazard map for the country, and one of the best this thing which is used by Bureau of Indian Standards. And we also, these are all our contributions in Earth System Science. We also use the GPS which you use in your mobiles for finding out how much the Indian tectonic plate is moving. So as you can see, these arrows are the tectonic plate movement, and this is our network. You can see, I just put the slide. People can go into it and look into it later on. If they want any details, there's one more talk on GNSS and its applications. They can go to it. But this is what we do. We find out the tectonic plate movement and we do research on it. This is the second one. And then we have a very good group which is works on climate change and its impact. We have experts in climate modeling. The lecture after me by Dr. Sajani Surendran is from this research area. So you would hear her. And then this is one thing which I thought we should mention, greenhouse, which also relates to students. We have greenhouse GHG network, greenhouse gases network, which is of WMO standard. We have 4 stations. One again we have in Hanle in Ladakh, where I showed you the telescope. We have a GPS station also here.
Yes, it's on. I can see.
This is my last slide. I'm almost done.
Okay.
So we use this to find the carbon. What are the main? See all these red which you can see through our model. These are the main countries emitting lot of carbon. So this is one of the other good one. And then coming to data science supercomputing group, as I've already said, we host CSIR supercomputing facility. Hello, you can hear me?
Yes, ma'am, we can hear you. You can continue. It's screening also.
Okay, supercomputing, because my mouse is not moving, so.
Okay, no. It's audible and visible both.
So this is the glimpse of data science supercomputing division, where we do research on cybersecurity, cryptography, and also domain agnostic AI and ML. And we have recently 1.2 petaflop system was donated by AMD for COVID care research. And that's it. That's a glimpse of our institute. You can see on our YouTube videos if you want any more details on what we do and all that. All that is there on our YouTube channel. And you can also see for the students, there is CSIR Jigyasa YouTube channel, that is CSIRs. So that also has a lot of this thing. And we have an academic program for research PhD students, and a Spark program for students of masters and all who wants to do engineering people who wants to do internship. Thank you.
Thank you, ma'am. Thank you very much for this informative lecture and letting us know how data science and machine learning is playing a pivotal role here. Thank you very much once again. Now we have Dr. Sajani, who will give us her talk on physics of the Indian summer monsoon. But before that, I would like to introduce Dr. Sajani. She obtained a PhD in atmospheric and oceanic sciences from Indian Institute of Science. Before joining 4PI, she worked as a postdoctoral research fellow at Florida State University and as a research scientist at Meteorological Research Institute of Japan, and also as scientist at Space Physics Laboratory of VSSC ISRO for several years. She has made important scientific contribution in advancing the understanding of Indian summer monsoon and variability and monsoon simulation by climatic models. Her research also focuses on the impact of aerosols on monsoon and reliable climate change projections of monsoon and extreme events. Using state-of-the-art climate models, she has authored over 30 scientific papers and 4 book chapters and guided several PhD students. Thank you for doing this with us today, ma'am. The floor is yours.
Thank you, Pavithra. Thanks for the introduction, and good morning, everyone. My slides are visible?
Yes, ma'am. You have to speak a little more louder. You're slightly less audible.
But you can see the slides.
Yes.
And it is in the presentation mode, right?
Yes, ma'am.
But I'm unable to move the. So the title is Physics of Indian Summer Monsoon, And in this talk, I would like to convey whatever I'm trying to in a manner in which is others can comprehend it easily. So let's discuss the following. We start with what is monsoon. What do we know about our monsoon? That is the summer season monsoon over India. And why is the monsoon so important for Indians? And why do we study the physics of the monsoon? How do we observe the monsoon? To study, the basic thing is to observe it, and then we need to model it. Can we predict the monsoon? Yes, we can, but not perfect yet. That's a food for thought. And then I'll end with a demonstration on 2021 Indian summer monsoon simulated by a computer-based model here at the CSIR 4PI. So it's a very familiar term, monsoon, which is actually derived from the Arabic or Hindi word Mausam, which means season. This term was first used by Arab sailors to denote the large change in the direction of the winds with the seasons, which they observed over the Arabian Sea when they came sailing towards India for so is it visible now?
Yeah, it's working.
Yes, ma'am. It's fine.
Okay. So over the Indian region, the sailors observed that the winds are strong and blow from southwest. That is, if you take the top as north, bottom as S, south, then it is from southwest. The winds are always stemmed from the direction it comes from. So southwesterly in summer, as shown by this red arrow, and whereas they are from the opposite direction, that is from the northeast in the winter. But for Indians, it is experienced as a marked seasonality in rainfall, which is of far greater interest to us than the winds per se. With the advent of summer season in June, we start getting abrupt but sustained, very sustained. It's not 1 or 2 days of rainfall, but a season of persistent rainfall, which lasts almost till the end of September over many parts of the country. So in common parlance, the monsoon is thus the rainy season that comes in every summer without fail. But you have to notice that it is not always with the same nature or gusto. No two monsoons are similar. So the commencement of the rainy season is termed as the onset of the monsoon, and the end of the rainy season is termed . So our land, the Bharatvarsha, is actually synonymous with the monsoon subcontinent. The term, since the pre-Vedic era, monsoon which are recited to propitiate rains for the well-being of the people. Even now, the finance minister, mostly even last finance minister's speech starts with or mentions the monsoon. Historically, monsoon rains are considered to be a unique feature of this land. This is considered as the monsoon subcontinent. The idea of India has thus been defined by the monsoon, a season which brings torrential rains to the plains and mountains of the subcontinent. Awaited anxiously by the millions of Indians, the monsoon turns India into a soothing green visher year after year and fertilizes our sprawling farms and orchards. So no wonder that the monsoon is associated with abundant joy and love in Indian culture. India's agriculture, art, music, dance, literature, films, and religious texts are replete with magical vignettes of monsoon rain. So the life of plants and animals as well as human beings on this subcontinent is tuned to the annual visit of the summer monsoon. You can see this life, how the life unfolds in a rainy season. The new year, according to Indian calendar, is sometime after the spring equinox, that is March 21st. Equinox means when the day and night are equal or the sun is just overhead the equator. So this heralds the beginning of the hot, dry summer season for India, which precedes the monsoon rains. For example, this is a site of how the day starts during a New Year day, that is the Vishu in Kerala, which is mostly celebrated in mid-April. This season is traditionally said or called as the pre-monsoon season. At the height of this long dry season, many trees burst forth into bloom as their seeds must be ripe and ready to sprout with the arrival of the monsoon rains. You can see that with the burst of the monsoon, many ephemerals flower with the first rains. Medicinal herbs like shatavari sprout soon after the first rains. The spectacular dance of the peacock characterizes monsoon season. As rivers and streams swell with the monsoon rains, many fish swim up the current to spawn in pools near river origins. So life is in sync with the monsoon. Our people are not left far behind. We also celebrate monsoon in various forms. For example, Dahi Handi festival on Gokulashtami Day, which is a grand full moon of the coconut day. Another site is a Nehru Trophy boat race in the Punnamada Lake of Kerala during the height of the monsoon season. So the monsoon is so much entrenched into our life. So this is actually the part of the seasonal cycle, or Ritu Chakra, we call it. In India, monsoon comes every summer. So broadly, the 6 Ritus in India can be considered Vasant, Grishma, Varsha, Sharad, Hemant and Shishir. So the Varsha season or the rainy season comes from June to September. The seasonal cycle itself is not the same at different parts of the country. Why is it so? Because the seasons depend on where your place is located and on the globe with respect to the equator. Thus, there are slight differences in the dates of the onset of the monsoon as well as its retreat over different parts of the country. So to know that, we need to know latitudes and longitudes. These are lines of imaginary lines that encircle the earth in either south north or west east directions. You can see the left panel shows the latitudinal lines and the right panel shows the longitudes. So if you look at the globe, top denotes the north pole, the bottom denotes the south pole, and then west and east on the left and right. Then latitudes are south-north oriented horizontal lines. Equator is 0 degree line. It splits the earth into 2 equal halves. The northern, denoted by the blue lines, and southern hemispheres are denoted by the red lines. There are 90 degrees to the north and 90 degrees to the south of the equator at an interval of 1 degree if you take. So the longitudes are vertical lines. Okay, there are 360 lines if you plot them at 1 degree interval. They connect the poles, and you can see they also split the globe into 2 halves. The western hemisphere denoted by the red lines and the eastern hemisphere. But the latitudes, the left panels where you are with respect to the equator, has so much importance for your Ritu Chakra or the seasons. We'll come to that. We all know that the earth rotates around its axis. How long does it take it to complete one rotation? 24 hours. If you look at the globe from the top, that is the North Pole, the earth is rotating around the North Pole in a counterclockwise direction. This is a non-fact. We also know that the earth revolves around the sun in an orbit. How much time does it take to complete one revolution around the sun? 365 days or 1 year. But one feature you should notice that this is not a circular orbit. It's rather elongated or an elliptical orbit. So the sun is not at the center of the orbit, but rather it will be at one of the focal points. That makes the earth closer to the sun in every January and a little bit further away from the sun in every July. So we expect the earth to be the warmest when it is nearest to the sun. So do you think in January, the northern hemisphere where we reside in, where India is it the warmest in January? No, it is not. We know that it is our winter time. So the seasons are caused by some other factor. What is that? Let us see. So the basic source of energy, as we all know, for atmosphere or any Earth system sign is the sun. Solar energy is transferred to Earth atmosphere system by radiation. There is no mass exchange, no medium required, and radiation moves at the speed of light. So this movie shows you the latitudinal distribution of incoming solar radiation and its effect on energy received at the Earth's surface or by the surface of the Earth. The maximum is received at the equator, where it is directly hit at 90 degrees, and minimum at the poles, because they are a little bit farther away from the sun if the sunlight is coming from the right side. This is because the solar beam spreads over a greater area as you go higher latitudes away from the equator. And another slightly technical thing is the beam depletion, or the energy gets depleted, or which we call as attenuated by the atmosphere or any constituent. That depletion is more if the beam is slanted or towards the pole rather than straight, which is the case with the equator. So that was the ideal case if the axis was vertical. But we all know that the axis of rotation of Earth is not vertical, it is not straight, it's rather tilted. So this picture shows the tilted axis of rotation, which is the vertical line, north-south line, and the axis of rotation is tilted by 23.5 degrees from its vertical. Okay, if the sunlight, let's assume that the sunlight comes from the right, as in the case of July in the last slide, then 23.5 degree north is most northerly latitude at which the sun can be directly overhead. So the North Pole is actually facing towards the sun. This is called, this 23.5 degree north latitude is called the Tropic of Cancer. The region between equator, this dashed line, and this Tropic of Cancer is called the Northern Tropic. It's called a tropic, region of tropic. The opposite happens in January if the sunlight was from left side. Okay, you can see that the globe can be tilted the other way, and then the South Pole will be towards the sun, and the sun will be overhead at 23.5 degree latitude in the southern hemisphere. This is the Tropic of Capricorn, and the region between the southern region between equator and Tropic of Capricorn is called the Southern Tropic. So the southern and tropic and northern tropic together, this banded region is called the tropics, where all the monsoons of the world occurs, including Indian summer monsoon. So when we come, now let us return to the tilted axis. Axis of rotation is tilted. So we know that when sun completes one revolution around the sun in its orbit, it completes 365 rotations as well. So with this tilted axis. So when it is June 22, that is solstice, we have seen that it is the position where it is farther from the sun. That time North Pole is facing towards the sun and South Pole away from them. In December, it is the opposite. South Pole faces the sun and North Pole is away from the sun. So what shows is the most part of the southern hemisphere receives more sunlight, and the northern hemisphere, actually the North Pole and the region of the North Pole around the region actually gets 24 hours of darkness. So this tilt explains the why it was winter for northern hemisphere or India and summer for the southern hemisphere. But when the Earth moves to the halfway through June and December, that is in March and September, this tilt of the axis doesn't cause any pole, neither pole to face towards the sun or away from the sun. So the tilt doesn't matter. So there, every part receives equal energy. For example, the sunlight falls on the equator and other places at 90 degrees and equal nights and equal days will be there. Coming back to December, you can see that the South Pole is having 24 hours of light, and the straight direct hit of the sun's rays will be at a Tropic of Capricorn. Okay, so this is the summer for southern hemisphere. When it is summer for southern hemisphere, the North Pole is having 24 hours of darkness. Same is the case with the some other solstice in June for northern hemisphere for India, for example. So when we observe the revolution of Earth around the sun, what we see is the season for the northern hemisphere moves from March, that is the springtime, to June. It's summer, then it's September, it's fall, and then December, it's winter, and then back to its spring season. So it's a cycle or the Ritu Chakra. That's what it is. Now coming to the solar radiation. So we understood that the seasonal cycle plays a role. The tilt of the axis of rotation is the main factor which causes the seasons. Now, if we get the solar radiation, how it is affecting the atmospheric dynamics. So that is, dynamics means the movement of the atmosphere, which causes the weather and climate. So the solar radiation, when it comes to solar radiation, the sun is very hot with an effective temperature around 6,000 kilometers. So according to the certain laws in radiation, the wavelength of maximum emission, that means a hot radiating body emits radiation at a particular frequency, which is inversely proportional to the temperature of the radiating body. Hence, the solar radiation, its temperature is too high, but the emission will be at a short wave. That is the maximum at 0.5 micrometers, okay, which is the visible spectrum. We can see it, it's a red light. Red light is in that frequency, wavelength. So this solar radiation is called a short wave radiation. The Earth is much cooler, okay, 288 Kelvin, and hence it emits radiation at longer wavelengths, okay, and that will be from 3.5 to 50 micrometers with a peak around 10 micrometers. So why is it important, the wavelength of the emission? Because the atmosphere is almost transparent to the short wave radiation. The solar radiation just comes through the atmosphere without much of a, technically not much of a attenuation. There are slight variation, but practically you can say it as it is almost transparent. Hence, that radiation which comes to the Earth atmosphere system, it gets absorbed primarily at the surface of the Earth, be it land or ocean. Earth, after absorbing all that, it emits its radiation, as I said earlier, in the long wave. Thus, even though the basic source of energy is sun, the atmosphere is heated from below. Hence, the temperature of the atmosphere, see, you are heating something from below, the temperature of that decreases with height. How, up to what height it will decrease? It will decrease up to the tropopause, or the top of the first layer of the atmosphere. This is called a troposphere. So, over India, the tropopause is around 15 kilometers. This is the layer where all the weather activities, clouds, tornadoes, cyclones, anything, if all that, they all take place in this layer. So the Earth's atmosphere is a thin band of air made of several layers. Troposphere is the lowest layer, that is the most important layer, but there are layers above it based on vertical variation of atmospheric temperature in them. Okay, so I'm just showing the vertical temperature plotted for two regions, that is our Bay of Bengal and Arabian Sea. These are the observational campaigns done by scientists on Indian ship of ORB Sagar Kanya, that is BOBMEX and RMEX, BOBMEX over Bay and RMEX over Arabian Sea. Both shows, see, this is the x-axis, that is temperature is plotted. From left to right, it is from low temperature, cold to hot, and you can see that at the surface level, that is 0 kilometer, it is 30 degrees centigrade if you take it. Then it reduces, that means it goes left with the height. And at tropopause, that is the line I have put a dotted line, there it is a minus 80. Okay, so the temperature just decreases. The same is the case with Arabian Sea, the atmosphere over Arabian Sea also. So in the lower layer of troposphere, temperature decreases with height. In the second layer, you notice there is above the tropopause, there is a layer called a stratosphere. There you can see the temperature is increasing with height. Okay, it just goes right to the right. So that why does it increases? Because there is a ozone is present in abundance in the stratosphere, And that ozone has the capability of absorbing the ultraviolet part of the solar radiation. You know that ultraviolet is harmful for us, so it's a good thing that the ozones absorb it. So you are also aware of the ozone hole and how it is dangerous for people if the ozone hole persists or grows. So stratosphere is also, that is just above the troposphere, very lower part of the stratosphere. That is what the ozone present in that layer. And this movie shows, so we know that we get maximum, if we get maximum solar radiation at a surface, for example at the equator, what happens? That area gets warm, the atmosphere or the air gets warm, heated up. Warm air is light, okay? They feel light. Lighter air, what will happen? It will go up because they will have that buoyancy or the ability to rise up. If air rises up, the pressure also reduces, okay? Because atmospheric pressure is nothing but the weight of the air column above. So warmer areas, they make lower pressure areas. So when the equator is sustained manner gets very high solar radiation, it actually converts it into a low pressure area. Okay, so the warmer areas on surface have lower pressure. The warmer air that rises will ascend. It will ascend till when? Till it gets cold or it is not having the buoyancy to ascend further. That is when it gets cold. What will happen then? It will diverge to the surrounding. It goes up, diverges up in the surroundings at the upper level. At surface, the equator is persistently getting heated up, right? So the surface, more air from the surrounding. If you just keep on, the air goes up, it will become a vacuum. That cannot be, okay? So when there is a vacuum, other things will come and fill it up, right? So at surface, more air from the surroundings will converge into the warm low pressure area at the surface. This will continue. This vertical cell will continue, and the low pressure area will grow in strength to strength because it's getting heated up also. The solar radiation is hitting on it in a continuous manner. So this is called a trough. And this trough, elongated low pressure area, becomes a convergence zone. Remember, all this happens in the tropics. So the convergence zone in the tropics is then called tropical convergence zone. Okay? Or if it is because of convergence between southern and northern tropics, I told you that. If that low pressure zone comes in between the air masses from the two tropics meet and rise up, it is called the intertropical convergence zone. Okay? The ITC study. So this figure shows the low pressure area, elongated trough, and how the air converges. This convergences of air, that is called winds. Tropical surface winds are associated with a trough at the equator. This is an idealized situation. Everything what I am showing is an idealized situation. So if you take a cross section from north to south like this and tilt it in the horizontal way, that is, the left hand side is north, the right hand side is south, and middle is the trough zone or the rising or convergence zone. Okay, so what you see is a very strong, vigorous ascent. Okay, vigorous ascent of air that creates the clouds. Okay, so how do we get monsoon rain? Through clouds, yes. When a mass of moist air or vapor rises above a certain vertical level, okay, it was a moist air till then in the atmosphere, moisture saturates. That means in a unit volume, how much moisture you can hold, that overshoots. Then what happens? Then condensation happens. Once it is condensed, it is not a vapor anymore. It's small droplets, okay, liquid. And clouds are thus formed. So clouds are basically a mass of water drops or ice crystals suspended in the atmosphere. In the beginning, this water in clouds is in small droplets. Okay, these droplets are so light that they float in the air. Subsequently, these droplets join with others and turn into larger drops. Then the gravity causes these heavy drops to fall down to earth. We call these falling water drops the rain. In tropics, rain-giving clouds are typically 4 to 6 kilometers in horizontal extent. You can see some of them. Often we get thunder showers with such single clouds in the pre-monsoon season, dry season. Moisture availability is small or controlled. And that is the season of April, May. But during monsoon, the system, the beast is so so huge. Okay, in that sense, the clouds are get organized into systems of much larger strength and spatial scales. Okay, basically there are three scales: mesoscale about 10 to 200 kilometers, synoptic scale several hundreds of kilometers, and planetary scale thousands of kilometers. This is a satellite picture. With the advent of satellites, it became possible to literally see the cloud systems as white colors on the globe. This is a mesoscale system. Okay, this red arrow, larger than cumulus cloud, 4 to 6 kilometers, more than that, and but it is less than hundreds of kilometers. That's a mesoscale system. This is a synoptic scale system. Often the synoptic scale systems such as monsoon, lows, depressions contain several mesoscale systems. This is a picture of cyclone Gulab, which on 27th September of last year. You can see if the peninsula scale is 1,000 kilometers, this is around 300 or 400 kilometers. Inside that, there are mesoscale systems. So this is a synoptic scale system. Coming to the planetary scale system, a larger picture, you can see that these synoptic scale systems also, they get organized as embedded systems in planetary scale cloud bands, which can stretch over thousands of kilometers. See this is on 15th August 2016. This long band of clouds. So that is the planetary scale tropical convergence zone or the ITCZ. So we know that in March, low pressure area or the intertropical convergence zone, ITCZ, is very, very important. That is along the equator. It marches to the Tropic of Cancer and Tropic of Capricorn with the annual marching of the sun. So when it is in the reaches the equator in March, associated with that, the area of precipitation also develops, and that also moves with respect to the sun's march. And in June, it reaches the Indian region. You can see this movie. Okay, Indian region, area of precipitation over India. That is the monsoon for us. And that time, dry season is for southern hemisphere. In December, when it moves to Tropic of Capricorn, you can see the area of precipitation is for Australia and all those places. Summer for them, monsoon for them, and dry season for us. So what all this shows is Indian monsoon is a part of planetary scale ITCZ caused due to the annual north-south march of sun and solar radiation. Monsoon is basically the summer visit of planetary scale ITCZ to India. This we can also see in the onset phase, that is 22 May. You can see last year 2021. This is the ITCZ sitting over the southern tip of India. During the monsoon, it marches to the central Indian region. And then withdrawal phase, that is 8th October, it again goes back to the southern part, that is southern tip. So that is the march of that. And rainfall, we know the physics, we know how it happens. Now, okay, so for studying the rainfall and its variability over the Indian region, rainfall data for a large number of stations are maintained by India Meteorological Department, and using that we can see that. So if monsoon comes, is it the monsoon same throughout India? No. It is distributed in such a way that the west coast is having high rain, central Indian plains, Gangetic plain is having high rain, northeast is having high rain, but the southeast peninsula is not having that much high rain. And the northwest, the Rajasthan area, that also does not have enough rain. So there is a spatial variation. Why does it happen? Because India is designed to have this kind of a monsoon. India is the only country in the world which has the mighty barrier of Himalayas to block the passage of rain-bearing clouds that bring magical rain dance to India. That is, the Gangetic plains will be flooded with rain there. It is also surrounded in three sides by warm oceans, which makes the air above moist and ready to rain. So India is blessed to have the warm oceans around and the Himalayas, and also the Western Ghats that causes high rain over the west coast. So the first reference of the spatial variation of monsoon rainfall over Indian region is seen in Kautilya's Arthashastra. The annual rainfall, they observed that in the drier parts of the country is 16 dronas, which is a measure of capacity. In the wetter tracts, it is 1.5 times of that much. That is 24 dronas. It is 13.5 dronas in the Rocky Peninsula and 23 dronas in the Avantis. On the west coast, it is beyond measurement. The rain is immaterial in tracts fed with Himalayan rivers or canals or wells. Why would a society is so much interested in documenting all this? Because what concerns to us has been the variability of the monsoon rainfall. In addition to the spatial variation, the monsoon also shows year-to-year variations. So some years are droughts, some years are excess monsoon years, and within the season also how a monsoon evolves. There are active spells, means very high rain. There will be a stoppage of rain within the season also. So the two monsoon seasons show that they evolve in two different manners. So how they evolve, how they vary, that is very much of a big concern to us. So why further study monsoon? We know the monsoon governs the pulse of life for us. The nature of monsoon every summer is utmost importance to all of us and is of great concern. The question uppermost in the minds of not only meteorologists and farmers but economists as well is how will the monsoon behave this year? To answer that, you need to predict it. Knowing beforehand the nature of monsoon is essential for better preparedness, planning, and efficient management of resources. This demands that you know all of it, or at least as much as you can. Okay, in CSIR 4PI, we run a computer model, a climate model to simulate the monsoon. In this model, Earth is taken as a rotating sphere surrounded by a viscous atmosphere of many gases and water vapor. Tilt its axis with respect to the source of heat and light, freeze it at both ends and roast it in the middle. Cover most of the surface with water that sometimes freezes and constantly feeds vapor into the atmosphere. Condense and freeze some of the vapor into clouds of imaginative shapes and sizes and composition. Fluid dynamics governing physical laws expressed as basic equations. Equations I'll give in the next slide. That is used as the governing equation. To do this, you need to know the physics of the monsoon. Okay, these equations are then solved numerically to predict the future conditions of the atmosphere for each place over the globe, including because it's a global climate model, we can do this for all the places over the globe, but we'll our focus is on Indian summer monsoon. The governing equations are Newton's laws of motion in 3D, conservation of energy, that is the first law of thermodynamics, continuity equation for conservation of mass, dry air, moisture, other species. Ideal gas law is also applied. Then we predict the change in space and time of wind, pressure, density, and temperature, and a whole lot of other variables. So this figure shows the left panel, the left movie shows the simulated Indian monsoon of 2021 from January to December, monthly rainfall in green shading. Okay, so you can want to observe. It starts from January, so you can see that by June, April, June, the torrential rain occur over Indian region very beautifully. That is 2021. That goes from say May, June, July, August, and then it comes back down. Okay, so this is the march of ITC said or monsoon rain. So now coming to the right panel video shows the winds in vectors and the strength of the winds in shading. I have started the talk saying that the sailors or the early people used to identify monsoon in terms of winds. Winds show a reversal in its direction. So this also we can see from the simulated 2021 monsoon. Okay, so it starts from June, now April, May, June. You see that the red shading on occurs over the Indian region. So this is what the simulated monsoon is. And as far as the basic features like this can be simulated very well, there are issues, there are challenges to meet when you want to forecast the exact amount of rainfall that will occur at any exact place. There are challenges involved, and we continue our effort. The mantra is keep up the effort. So I end with that. Thank you for listening, and thank you, Pavithra.
Ma'am, the pleasure was mine to listen to such a beautiful lecture. And I must definitely say that every student who would have listened to this would have understood pin to pin what you have explained today. And really, it was an experience. Thank you, ma'am. Thank you very much.
My pleasure.
We shall conclude this session by saying tomorrow we have another session on the topic artificial intelligence. So students, please do log in tomorrow at the same time, 11 o'clock on the same channel. Until then, please do like, share the video and subscribe to our channel. Until next time, goodbye, take care and stay safe. Thank you. Bye-bye.
Bye.